The last thing I want to talk about in this section is arguments. Now, I am talking about a mathematical argument and not an argument like you would have between siblings or parents or something like that. In a mathematical argument, you have a set of statements called premises, and you'll have another statement that's the conclusion. So in order to have a valid argument, you have to have a particular logical form where if all of the premises are true, it's absolutely impossible to have a false conclusion. So if you make true premises, then your conclusion has to follow if it's valid. We'll see in a later section there are plenty of arguments that do not have a valid form. That even if the premises were all true, the conclusion does not necessarily have to follow from that. So we can use Euler diagrams to help us with these arguments. So if you have the statements for the premises, no psychologist can juggle, all clowns can juggle, and then those dots, that means therefore. That's the conclusion. Therefore, no psychologist is a clown. Well, let's first start by drawing no psychologist can juggle. So here you would have a psychologist circle and a juggle circle with no overlap. Then the next statement that says all clowns can juggle, that means that all the clowns need to fit inside the juggle circle. And so that would look like this. The all part of those statements always goes in the smaller circle. So all clowns would be a small circle inside the juggle circle. Then the conclusion is that no psychologist is a clown. So if you have an item that's in the psychologist circle, is it at all possible for that to be in the clown circle? And in this case, there's no way for us to put a dot that's in both the psychologist and the clown circle. And so that would make this a valid argument. It absolutely forces us to draw the conclusion that there are no psychologists who are clowns. You'll get used to using these diagrams as you work through the homework and as you look through the other examples in the textbook. Along with our study of arguments, we can have this idea of transitive reasoning. And that's where you're going to have a series of these premises that connect. I think of these as dominoes, where one is going to hit the other, which is going to hit the other. Or if you read the childhood book, If You Give a Mouse a Cookie, that's actually a great example of transitive reasoning. If you give a mouse a cookie, he'll ask for a cup of milk. If he asks for a cup of milk, then he'll want to look in a mirror. And so it's just going to build throughout the whole story. Those are transitive reasonings. So here, when we're drawing these, all fried foods are greasy, all greasy foods are delicious, all delicious foods are healthy. Notice that we're going from fried foods to greasy, and then greasy to delicious, and then delicious to healthy. We'll draw an Euler diagram here with our nested circles. So we start with our fried foods all fitting into the greasy circle. And then all of our greasy circle will fit into the delicious food circle. And then all of the delicious foods are going to fit into the healthy food circle. In this case, if we knew that a food was fried, it would have to go inside this little circle here in the middle. And by being in that little circle, you're automatically in all of these other circles. And that means that all of the fried foods would also fit into the healthy foods. Now, this is a valid argument. That does not mean that it is true, because at least one of these statements in the premises is false. All delicious foods are not healthy. There are some delicious foods that are not healthy. And so since we have a false premise, we could have a false conclusion here. But that's not what validity is saying. A valid argument simply means that if all of the premises were true, then the conclusion would have to be true. And this is an example of an argument that would be valid.